Do you guys have any question before I start? Yeah. So, so first of all, I have like graded most, like I think all of you, like one or two of them are left of exam two. Um, I'm feeling a little bit better actually from the since the morning. Um, on Friday, it should be an in-person class, and I'll give you guys back like your exam two back. So maybe be in class on Friday. So today, November 6th, I guess. Yeah. So Friday, I'll give you guys your exam two back. And on what? On Friday again, you guys will have your quiz five. This will be on chapter nine. Only chapter nine, okay? We're gonna start on chapter 10 today, but it's not gonna be on the quiz. Again, on quiz five, it will be a group quiz. Okay. So you guys can talk to anyone in some sense. Like group quiz doesn't mean like uh the groups that you have in in your project. It means like whoever sitting next to you or whoever. Like you can even ask me. I'm gonna try. I'm not gonna give you the answer, like the actual answer, but I'll help you if you ask me. But you can like ask anyone. You can talk to people during the quiz. You can like if you want, you can sit next to someone else, or it's up to you. But one thing you should remember, okay? So what happens if I give group quizzes? Um, Last semester, I also have done the same. Like I gave people like, hey, you guys will have like group quizzes from the start. So what happens is like most of you think like, okay, it's not an individual quiz, so why not? Well, I don't need to study. I'll just be there. I'll figure it out. I'll wing it, right? Yeah, I get the sense of it. Like, yeah, if it's a group quiz, like you're allowed to like talk to the people, yeah, maybe you'll be able to wing it. But you have seen like all the quizzes are. It's not like you're gonna get the whole class time, right? It's like gonna be 10 minutes, 8 minutes, or something. So group quizzes, you will you can talk to your friends, but it's not like you will not have like that much time. So only thing you can talk to is like about the important stuff, maybe like, hey, am I doing this right? This is the way to solve it. Maybe the someone will be, yeah, this is the way to solve it, and maybe you can compare your answers. But apart from that, like if you want, like do whatever you want in your group quizzes, but you'll. I'm just saying, like you'll not have enough time to wing it. Okay,
I have an exam on Friday. Oh,
exam, then you can take it like some other day next week. Wait, like Emma, are you talking about like? Am I saying like you're gonna have like an exam
no.
on this Friday?
Sorry, I was talking about a different class. I didn't realize I wasn't muted.
Okay, 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 okay. Uh, any anyone else? Any question? Any regarding projects, quizzes, exams, anything? Okay, okay. If not, then sorry about that. I'll literally cough the whole class. Okay, I'm sorry about that. So chapter 10, we're gonna start this chapter today. So this is mainly probability, okay? And so this chapter is like the basic probability definitions, a couple of examples. I think if you have seen it before, that's also good. Like if not, it's like pretty basic stuff. You'll get it. Um, if you remember on chapter one, okay, on chapter one, we talked about SID. So SID means Simpson's Index of Diversity. And there was like a probabilistic term there that we didn't like explain that much because we didn't introduce one like probability before. That's why. So if you um, go through this chapter and go back to that SID on chapter one, you will find like what should I say? That term is like more meaningful. Okay. What else? Like probability, we do need this. I'll talk about that. And the next two chapters are also like probability chapters. Like they're gonna be like different aspects of it, but still they're like related to probability. And those who are taking 152 after this, the first, I guess, the two chapters in 152 will also be probability. So if you don't know anything about this probability, about like the basic stuff about probability, then this is really important. If you know some stuff about probability, then you're all good. In 152, you'll be fine. And hopefully here you'll also be fine. You'll do great. So so the background of it, like, so I should call it what? Motivation, maybe. Okay. So the motivation, all the coughing, heavy breathing. I'm sorry about that. I have like because I'm sick. Um, motivation is I can say randomness. Okay. So in biological models, ecological models, whenever whatever you're talking about, there are a couple of terms in those models which is associated with randomness. So you are not totally certain that it will happen. It might happen. Even if it does happen, it might happen down the time, like after 10 years, after 1 year, after 2 years, it might be something else. Like so they're like randomness throughout like any biological model. So to calculate those randomness or evaluate those randomness, what we need to introduce is probability. Whereas you cannot say for 100% this stuff will happen, or you cannot say for like 0%, that means this stuff will never happen. What happens is like it's between that 100 and 0. So maybe there is a 40% chance of this stuff happening, like some kind of like an event. Maybe there is like an 80% chance of this sometime happening, but not totally 100%, not 0%, 80%, 60%, whatever. So these probabilistic terms goes into those math models. Okay, so I should say randomness. What we want to do in this chapter is to quantify this randomness. Quantify means like calculation or like evaluating. It's like a fancy name, nothing else. And let's name randomness as another fancy math name, stochasticity. Okay, another fancy name for randomness. We want to quantify randomness. Okay. So this is what we're gonna do in this chapter. Let's go through like an example, what I mean by this. So in like any kind of natural settings, there will be randomness. So let's say uh, gender of offsprings of black bears in the Smokies. Okay. Okay. So in the Smokies, we want to find like kind of like calculate what should be the gender of the offsprings of black bears. I wrote it wrong. Maybe in 2024. Okay. So here we need probability because in some sense like you cannot like say for certain like a certain like 100% like a black bear will have like a male or female cub. That's not possible. Like it can have a male or female, but you cannot say it for sure. Like, okay, we have like 100 black bears. That means it's gonna be like 50 male black bear babies. I mean like cubs. It's not possible for you to say. And stuff like that. It's like all over math models, like biological models, like so many terms which are like not at all 100%. Like you cannot like force, cannot like determine them like indeterministically, like, and that's where the randomness comes in, stochasticity, same word actually comes in, and you'll have to evaluate them, and based on like what kind of probability you assign them, the model starts to work. And these values vary because of like other parameters, like let's say like temperature, um, weather, even though they're kind of the same, like climate change, other like other species invading them, like what kind of food are they are getting, how many black bears are there in that area. If there are more, that means like there's like a competition between them. If there are like a scarcity of the food, even though this does not seem like, what should I say, like totally relatable to the gender offspring, but they might be. There is a chance, like just because like maybe the black bears are dying, so there will not be, I guess, like any offspring. Like there will be no babies there. So this stuff comes in, and these are important. Okay, so this is the motivation. So why do we need this? So I'm gonna write like a couple of basic um, probability definitions. So whenever I'm saying basic, it doesn't mean like it's easy stuff. It just means like the fundamental definitions. First one is the experiment. So normally, I think I think you have heard it before. Like if you're talking about like probability, everyone talks about like flipping a coin, okay, or rolling a die, or picking a card from a deck of cards. And this stuff, like this whole thing, flipping a coin, the possible outcomes that's possible, like head or tail, rolling a die, that means 1, 2, 3, 4, 5, 6. Picking a card from a deck of cards, that's mean like 1/52. That's mean like we have like 52 cards. You're like picking just one card out of it, the probability is 1/52. So this whole thing, this deck of cards, this flipping a coin, rolling a die, this whole thing is called experiment, and the possible outcomes are also included in it. Okay. um, it's like, and also like if you want to have like real life example, even though flipping coins are a real life example, who do you play in the next game? I forgot. We played against Kentucky, right? So let's like the ball football team. Okay. Let's say that we didn't play against Kentucky. Okay. And so now, and you want to, and you were like really, not like me. I have a friend, not like him. It's actually not like me, who like bets a lot, DraftKings or something. I don't know. So you want to bet on one of the teams, Tennessee Balls or like the Kentucky team. Um, so if you uh, talk about like any football games, soccer games, there is always going to be a probability of which team is like more likely to win. Like what are the odds, right? People talk about that. So that's like that is probability. So if your team's record is good, they're winning the last match, like last couple of matches. They have like good players who are most likely to play well. They don't have that much injury. They have a good squad list. They have a good manager or coach or whatever. They have a good stadium. Blah blah blah. These parameters plays in when you're trying to calculate like a, of like a team winning or losing. Let's talk about another parameter. Like if Tennessee Balls are playing here in Neyland, they're more likely to win because of all the fans there. There are like 100,000 fans cheering for them. But if they're playing somewhere else, and let's say it's a smaller stadium, there are like a couple of hundred Vol fans there, and all the other people are fans of the other team. So they're kind of less likely to win that game because they don't have that much like even though they might win as a good team, but I'm saying the probability will go down when they're playing air matches. So, and this is in some kind of like, even though this is like games and like, um, you say like, huh, this is not real probability, maybe. Some people did say that in my last semester, but this is actual probability. This is like actual, um, this comes from like actual probabilitical, like mathematical models, the things you see in like DraftKings or somewhere else, I guess. So Tennessee Vols playing against Kentucky, that's the experiment. Okay, let me write the actual definition. We can list all possible outcomes. Okay. Then we have sample space. So let me go back to that coin flip. In the coin flip, when we talked about like having like maybe a head or a tail or rolling a die, 1, 2, 3, 4, 5, 6 coming up, this whole thing, this whole individual, if you group them together, it is called a sample space. Okay. So if you list all possible outcomes, listing all possible outcomes for an experiment is called sample space. Sorry, often denoted by S. Okay. And I'm going to say individual outcomes. We're going to give them a name. Maybe you haven't seen this name before, but we're going to, from for this class, we're going to start calling them elementary events. So not just events, elementary events. So in some sense, example, if you're flipping a coin, the sample space is head or tail, and this thing is called elementary event. And we're gonna say like, so head is an elementary event, T is also an elementary event, both of them. So if we group them together, all if we group all the elementary events together, we're gonna get the sample space. So I'm gonna say therefore sample space is comprised of elementary events such as this is E1, E2, dot 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 dot, En. So we have like n elementary events. You group them together, you get the sample space. Any question? Anyone? So example one, sorry, example one. So even though we have just solved it, it's still gonna ring. Where's the sample space of the coin flip? I'm gonna write it. Then we're gonna go to the next version of it. Solution is gonna be head or tail. Now the second version of the problem is sample space of two coin flips. So what's going to be the sample space if you flip two coins? So I'm going to give you guys a minute. Then I'll ask you guys randomly that what is the answer for this? Okay. Let's ask someone. Larry, are you there?
Yep. Would it be HHTT?
Are those the only ones, or do you think like there should be more?
I
Those
think
two
that
are those two are right though.
I think that's it.
Okay. Let's think about it. You're like almost correct. Like thank you though. I thought like you guys just logged in and like went somewhere else, which is normal. Okay. So Larry said HH and TD, which are absolutely right. So that means the first coin flip you get ahead. Second one is the same. So both of them are kind of the same. The first one is a tail, then second one is also tail. But what about this, Larry? Like head and tail and head. Do you think these two are correct?
Yep.
Okay. Yeah. Yeah. But the first pressure, you were right. Okay. So if you have like two coin flips, that's gonna be the answer. And thank you, Larry. Okay. Let's let's define elementary events properly. Okay. Even though we have been talking about this elementary event. Okay. Uh, describes only one outcome. So again, elementary event means just only one outcome, not the whole thing. Sample space means it has all the events, all the elementary events. An event, I'm for sure if you have read probability before, you have seen the definition of event. What we're gonna do is like we'll define event using the definition of elementary events, um, which is a bit weird if you haven't seen it before. But I'm telling you, the definition you have seen before and this definition basically mean the same thing. It's not different. So I'm gonna say multiple elementary events, one elementary event or none elementary events. All of them are events. So if you take like two outcomes, that will be an event. If you take no outcomes, that's also an event. If you take all the outcomes, even though that is equal to the sample space, that's also an event. If you take just one of them, that means it will equal to the elementary event. That's also an event. And if you take two of them, just like if you take like this one and this one, like Larry did, that's an event. But individually, they are just an elementary event. Okay, so that's the definition. I think you guys are getting it. I'm just like over explaining this. Okay. The notation. But if you don't understand anything, just let me know. I'll explain it. I think I will explain it a little bit better. So the notations we're gonna be using in this chapter. Elementary events. Smaller e. regular events. It's going to be capital E and enter sample space. As you have known, it's going to be S. Okay. So these are the notation. Now, another example. Suppose that a coin is flipped twice. Let E denote the event, where the first and second flips match. Okay. Solution. So what's going to be E for this? So I'm going to call Larry again. Okay, I'm sorry about that, but I'll call you because of one reason actually. So what do you think the answer for this should be?
So it's the event where the first and second flips match.
Mhm.
So then that would be HH and TT.
Yes, exactly. So the one that you answered previously is the solution for this one. And ironically, it's not like I'm writing this top of my head. I wrote this before. I would have like written this question right now, but you have answered it way before. Okay, thank you, Larry. I'll not call you new again in this class. Okay,
Sounds
you're all
good.
good. Yeah, you're all good. Okay, so that's good. Then let's another example. How fun. Okay, so suppose that a single die is rolled. Okay. So remember, dice means two dice, and normally a die is called a die. It's like, so you guys know what a dice is, right? Six-sided, 1, 2, 3, 6 marked thing. A die is just the singular form, and the plural form is dice. Okay. So I'm going to say what is the sample space. I'm going to write the answer here because I think you guys know about this. Sorry about that. Oops. The worst thing is like the student health center. They don't have any appointments. Okay. Single die. So single die, we talked about this before. S1, we're just calling it S1. 1, 2, 3, 4, 5, 6. Okay. So six-sided, each of them are marked 1 to 6. So the possible outcomes, if you roll it, it's like 1 or 2 or 3 or 4 or 5 or 6, which is like good enough, like simple problem. Now I'm gonna say suppose that two dice are rolled. Okay, so what is the sample space? So I'm gonna give you guys 2 minutes, solve it, and I will call on someone like randomly, okay, whoever I see on the screen. And if you have solved it, it's good. If not, I might call on someone else, or I might just help you go through how to solve it, how to solve this. Think about this for 2 minutes. If you know the solution, then just sit tight and chill. If you don't, then think about it. Okay, I think, I don't know. Sarah, do you know how to solve it? I think Sarah isn't here. Let's ask someone else. I don't know. Drew is here, right? Drew, do you know how to solve this?
Would it just be S1, 1, 2, 3, 4, 5, 6, and then S2, 1, 2, 3, 4, 5, 6?
So, okay. In some sense, I know what you're saying. Maybe it's right, but it's actually not right. Here, so this was like together, right? Two coin
Oh,
flips. So HH, HT, like so they're grouped in pairs in some sense. So that's gonna happen to this one too. Same process.
then it'd be like 1, 1, 1, 2, 1, 3, so on.
Do you know how many of them will be?
Uh, would it be 36 or?
Yeah, 36. It's gonna be 36.
Yeah.
I'll talk about that too. Okay, thank you. Drew.
Yeah.
You actually probably solved it right now, so that's good. I wouldn't have able to solve it maybe if someone was asking me this kind of question. Okay, so what will happen is like as they're like two dice, it's gonna have outcomes on like ordered like a pair, ordered pairs. So what I mean is like if the first one is one, let's say, like suppose, and the second one is one, that's one of the outcomes. Let's say the first one is still one, second one gives you two. The first one is still one, the second one gives you three. The first one is still one, the second one gives you four. Probably you're getting what I'm saying, right? And five and 1,6. So that's one row of outcomes, but there are more. You can say the first one is two, then the second one is one, first one is two, second one is two, first one is two, second one is three, this is four, first one is, and then 2,6. Okay, so that's like another one. Then let's move more like 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6. Yep. And so on, like dot 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 dot. So then it's going to be 4, 1, 4, 2, 4, 1, then 5, 1, 5, 2. So I'm just going to write the last one. 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. So the whole thing, I messed up. Let's write this better. The whole thing together is your sample space. And there will be 36 total outcomes. Any question for this one? Anyone? There should be a parenthesis here. No question. Okay. Let's ask another question then. if sum to 7. So I'm not writing the whole thing. So what I'm trying to say is like if the outcomes you find, if you add them, because they're like what? Pairs, right? 6, 1, 6, 2, 6, 3, 6, 4. So they're in pairs. So if we add the pairs, like 6 plus 1 will be 7. How many are there? Where and you have to write them explicitly. How many, which are the ones that will, if you take and if you add them, it will be 7. So I want you guys to find that. So let's name it S3. Okay. Um, let's ask someone. That's more fun. Um, Sean, are you there?
Yes.
Okay, start there. Do you have any idea how to solve this part?
I'm gonna be honest, I wasn't listening.
Okay.
What was the question?
Okay. I'm gonna ask you right now. So on the second part, what we did was like we took all the sample space when you roll like 2 dice. Okay.
Right.
So that's why it's like 1, 1. So you're getting like 1 from the first die, and the second one from the second die. So
Mhm.
like that. So what I'm saying on the third part of the question is like like which outcomes you're gonna get when if you add them together, the pairs like 6, 1, it will be 7. So 6, 1 is one of them. So what else?
I guess 3 and 4,
Yeah, let's write 3 and 4.
5 and 2.
5 and 2. You're right. Anything else?
I guess the reverse of those, 4 and 3, 2 and
Yes,
5,
yeah,
1 and 6, and 6 and 1.
exactly. Thank you. That's like totally right. And yeah, so that's the answer. And in some sense, this is a simple one. Thank you, Sean.
Yep.
So the thing is like I can make like construct these kind of problems, but maybe in a complex way. Like this kind of seems like easier. Like I can have like multiples of 3, multiples of 5, multiples which are just like stuff like that. Or if you add them, will it become a prime number or stuff like that? Like this, just, even though these are like not totally related to the biological problems that we are talking about, but I don't know, like fun thing to do. I think it's probability. Okay. Any question for this problem? Okay. Next one then. If you don't have any question. Multiplication principle. Okay. So what this principle is, it will calculate the total number of outcomes when you have multiple experiments. So let's talk about this one. This one. We had 2 dice. We rolled it. Each of them had 6 possible outcomes. But when you group them together, like you're rolling 2 dice like one after another, your total possible outcomes from 6, it was like 6 times 6, it was 36. And then let's talk about this one. 2 coin flips. One of them is just like 2 possible outcomes, head or tails. Head or tail. If you have 2 of them, like consecutive, like one after another, it's like 2 times 2 actually. So it's like four outcomes. So this multiplication rule or principle is true for any number of experiments and total number, an individual number of outcomes. So what you need to do is to like just multiply them to get the total number of I keep on saying like experiments, total number of outcomes. So by that I mean, if you have, let's talk about like just two experiments. Like suppose we have two experiments. And suppose that we have two experiments named, not named, I'm going to say E1 and E2. Okay. Rather suppose that E1 has M elementary events and E2 has N elementary events. Okay. Then the sample space. So I'm just like kind of stating what I said before 6 times 6 in like a general like way. So it is true for like any number of experiments. Space of the sample space of the combined experiment is going to be M times N. So you just need to multiply the individual number of outcomes. That's it. To get the total number of outcomes. So I'm going to say TNO. That means total number of outcomes. Any question? Anyone? Okay. If you don't have any question, then the class is over. I'm gonna see you guys on Friday, and hopefully